Really? Okay.
Hello, everyone. Welcome to Space Drafts 86.
Woo!
So for those of you who are unfamiliar, we are part of an international network of Astronomy on Tap locations, obviously here in Tucson. So Astronomy on Tap satellites meet in bars and pubs across the world to share really exciting astronomy talks with the general public. So we hope you're looking forward to today's. If you're new here, we have some great talks lined up. If you're returning, thank you so much for your loyalty to us. So let me go through the to-do list of all the announcements. So for those of you who are unfamiliar, we will have 2 talks today with a 20-minute intermission in between. Each talk will be about 20 to 30 minutes long. As you may have noticed by the fact that this train has been yelling at us for the past 5 minutes, we are right by an active train track. So if it ever does that and it becomes too loud to hear the speaker, any returners want to join me in what do we do? Toast the train, choo-choo, and take a drink. Normally our speakers will have trivia questions in their talks. I know Jeremy definitely will, and our second talk will actually be quite a lot of trivia, with prizes pending. I should have talked to you about this before. Yes, we have some prizes. So if you would like to answer the trivia question and come up and get a prize afterwards, feel free to do so with either Jeremy's or the second talk. We have merch. Please come check it out during intermission, after the show, whenever is convenient for you. We will also take donations. And I believe that is it as far as announcements go. Also, as you're getting drinks, please remember to tip your bartenders. Also, train, please don't start. I think that's it. So without further ado, I'm going to introduce our first speaker, Jeremy Dietrich, a friend and colleague of mine at Stewart Observatory, graduate student, and he will be telling us about discovering hidden planets. And now, take it away.
Woo! Thank you, everybody. Yes, I'm a graduating student this year. I actually be defending my thesis in about 2 weeks, so thank you.
Woo!
This is my first time doing this. I've been here for 6 years, and I've been doing the talks as a audience member for all this time, but I figured, you know what, might as well come up here and give the final talk right before I head out. I'm gonna wait. Hopefully it's staying away. So this is a little talk about a little bit about my research, but also just about a passion of mine, just finding more.
Choo-choo!
Choo-choo. There's 2 trains going by at the same time right now. That's never happened before. Yeah, so finding hidden planets, and basically just finding more out about the universe that we don't know. So I want to start from the very beginning. Very early on in our history as the human species, we've known about 6 planets. In order, we knew about Earth, which was supposedly the center of the universe at the time, and you can see that in this really nice geocentric model over here. Then there was the sun and the moon, but we knew those were not planets because they did things differently than the rest of the planets. And then the 5 that outside of the Earth that we knew of were Mercury, Venus, Mars, Jupiter, and Saturn. They all had their own celestial spheres in the sky, with the last one being the firmament, which was the plane of the fixed stars. So everything inside of that all moved around and orbited the Earth, supposedly, but the firmament stayed fixed. And the only change for many, many millennia, we knew about these as soon as early history was recorded, but the only change in all this was the heliocentric model from Copernicus in the 1600s. So the first hidden planet I'll say we discovered was Uranus. Uranus is just barely bright enough to be seen with the naked eye in a very good dark sky spot, and if you have really good eyes too. So it was not well known to the ancients because it was just hard to see, and also because it's so far away from the Earth, it moves relatively slowly. So they weren't tracking it constantly enough to be able to tell if it was moving across the sky. But there is evidence that it was first observed by the Greek astronomer Hipparchus in 128 BC. The first definitive observations that we know of occurred in 1690 with John Flamsteed in England. And there were additional ones in 1750 and 1769, but all of these observations thought that this was a star, because it was just sitting there relatively motionless in the sky. Uranus's orbital period, its year, is almost the length of a human lifetime. So it was not moving very much across the sky when it was first observed. And then it wasn't until 1781 with William Herschel and his very, at the time, strong telescope, was able to determine that Uranus actually grew in size when looking at it through different magnifications on his telescope, which told him this isn't a star. And so like, okay, I found a comet. This is great. This is what I've been looking for. Turns out, no, he found something even more rare than comets. He found another planet in the solar system. So this came to one of the first empirical formulas that we ever had for trying to find more planets. This is the funnily named tedious Bode law. It's two different astronomers came up with this together in the 1700s. And it basically matches the solar system predictions for all of the planets. It was just based on the numbers, just based on exactly the numbers we had, and they just tried to fit some simple formula to it. And this is the simplest formula they could come up with. So they started with negative infinity to get rid of that entire term altogether, and just basically make that 0.3 times whatever, nothing, to set it at the position of Mercury. And then they added in every planet after that with an increasing number, and got Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, and Uranus. And so it fits all the positions for the planets out to Uranus by about 3%. And so you can see here, it's very, very accurate up until about Jupiter. And we expect that there would have been a planetary body that would have been formed in the asteroid belt if it wasn't for effects of gravitation from Jupiter, et cetera, et cetera. But it actually does match the center of the asteroid belt really well. And so everyone was like, great, we can use this to predict where we're going to find the next planet. Because they figure, okay, there's probably something else out there, right? Like, who knows? So they studied Uranus for a while, and they mapped out its track across the sky, and of course accounting for Earth's moving around the sun as well, and we were able to fully publish the orbit in 1821. It's about 40 years after it had been discovered, which was more than half of its orbital year. But within the next 20 years, they found that it was already out of its expected orbit. It was not where it was supposed to be on the sky if it was just, orbiting the sun as gravity would be dictating on it, given the sun and potentially maybe Jupiter and Saturn are pretty massive objects, but there was something additional there. And so there was thought maybe there was another planet out there. Maybe something else out there of similar size or larger was pulling on Uranus and making it change its orbit. And that was Neptune. So Neptune was first unknowingly observed by Galileo with his telescope in 1612, 1613. Funnily enough for him, he actually would have had a really good chance of detecting it, of knowing it was a planet, because of how, in detail his observations were, but he had the unfortunate luck of it being basically at retrograde, or starting its retrograde motion at the time. So Earth was passing it in its orbit around the sun, and so it basically stayed motionless for months at a time in the middle of its orbit. And so he's like, okay, there's a star there, cool. So fast forward 220 or 30 years later, and multiple different astronomers around the world, well, around Europe at least at the time, were making calculations to the perturbations of the orbit of Uranus and calculating, using the math and everything that we have today to determine what the position and size of this planet would be that is perturbing this orbit, that's making us see something that is different than what we would expect. And so there were two different groups. There was an English group and a French group that both set their astronomers looking for the planet that was predicted. And the English group had outdated star maps. And so we're looking in the slightly wrong area of the sky. Not by much, just, less than your finger at full arm's width, wrong part of the sky with their telescopes, and couldn't see anything. French group had a newer star map. And so they were able to adjust where they were looking, and within a very small patch in the sky, they found Neptune within the first two nights they were trying to look for it. And there was a bit of a controversy because both of these, the English group ended up finding it, a couple months later, and so there were all this rush to publish and all that stuff that we've been hearing about in academia for forever, who gets credit for what and all that sort of stuff. But it ended up being that there was enough evidence for a joint discovery, and so between the two of them, all the groups together came and said, okay, we're gonna have Neptune. We found Neptune. They found Neptune. Let's just agree that we can be friendly about it. But yeah, so this was the first time they actually said, okay, we have data showing that something in our solar system is not where it should be, and we can use math and physics to determine what another planet would be doing to that planet in order to cause that. And that's how they found Neptune. So that's the basis of actually, in really what my research has been the last couple of years. But I want to go back to the Tedious-Bode law just for 1 second. It's wrong. Wrong. It's been found that, so there's a lot of debate about this, and it's been debunked, and it's found to be pseudoscience and all that sort of stuff. I just want to really get this said that this was just a numerical relation that people found in the 1700s and 1800s. It does not actually predict anything about what we would expect to see across general planet systems across the universe. It just happened to fit this one system for a subset of the planets that we knew. But it was the first attempt at saying, okay, how can we use the math and numbers we have to, go about and predict where we would see the next planet? And that brings us to exoplanets. So this is one of my favorite artist renditions. This is the Kepler Space Telescope, and just a multitude of the planets that it ended up discovering across its lifetime. But first, I'm going to do a trivia question, and this is slightly leading, so don't worry. Which of the following exoplanet systems have been claimed to be the first planetary system discovered? Gamma Cephei AB in 1988, PSR 1257 plus 12 BCD in 1992, 51 Pegasi B in 1995, or D, all of the above? Raise your hand. You in the front, you I saw.
All of the above.
That is correct. It was all of the above. So, please come and get your prize at the end of the show. But yeah, exoplanets were not easy to find originally. There was not a lot of evidence or data for them, other than the fact that we knew we had planets in our solar system. So, could there be planets around other stars? And it turns out that yes, although some of the data was for Gamma Cephei AB was retracted, and so they had to pull the discovery back and then rediscover it later on. PSR 1257 plus 12 is a very weird star. It's a remnant of an old, much more massive star, and it was found with the way that we still haven't found very many planets that around stars like that in the universe. The first one that was definitively like, okay, this is a similar planet to the ones in our solar system found around a star similar to ours, was 51 Pegasi B in 1995. That's the one that got the Nobel Prize a couple years ago for the discoverers. But all of these have claimed to be the first planet ever discovered. So yeah, they started being discovered about 30 years ago. It was really slow going at first. We didn't have necessarily the best technology. We were, it was cutting edge at the time, but it was still hard to get that signal because we're watching something, billions and billions of miles away, just barely changing the properties of the star it's orbiting. And so it was very hard to do it at first. It was very slow going. You can see this is the number of planets discovered per year as we go forward. And it was less than 100 a year until about 2010. So it was every new paper coming out was like, oh, we found a new planet. It's like, whoa, that's so cool. Like, there's so, we're just getting the tip of the iceberg here. So then, the 2010s was really what ushered in this new age of, the golden age of exoplanet discoveries. And that was with the Kepler Space Telescope. That's what Kepler gave us. We found hundreds and hundreds and hundreds, thousands even in 1 year, of planets from Kepler. And that was really what started this, ushering us into this age of where we have so many planets now, we can at least understand what a general planetary system might actually look like. If we were just look at any star and look for planets around that, what would we expect to see? So hopefully this video, whoop, this is a video of the some of the planetary systems that Kepler has found. It's going to zoom out in a second and just show you even more, but I want you to look at the solar system here. This is just the inner 4 planets of the solar system, so Mercury, Venus, Earth, and Mars. And then all these other ones are planets orbiting their own stars, and you can see just the variety of types of planets and planetary systems that Kepler discovered. There's planets that are as hot as lava, just constantly. Like their entire surface is, if it was rocky at all, was just lava. There's some that are the temperature of Earth. You know, if they were solid there, they might have life on them, for example. There's a lot of them that orbit very, very close in to their stars. Things going around really, really, really fast. There's some that orbit really far away, and even farther than the Earth or Mars does. But this entire suite of planets is what we can get the data from for where we go for next. So currently, there are over 5,000 known exoplanets. There also are another maybe 6,000 or 7,000 unconfirmed candidates from different surveys still ongoing right now. And so there's a lot of work being done to try to verify all of these candidates, but it's going to take a while. But with this data from Kepler, with these thousands upon thousands of planets Kepler has found, we can actually study their entire population and understand at a general level. Shoot you again. So we can understand the data that we get from these planets and can understand what types of planets we expect to see, what their physical nature is like, how far away they orbit, and just what if we were to look for more planets in these systems, what else we would find. So yeah, there we go. So we can now predict, this is what a lot of my research has been on, we can predict additional exoplanets in a given system by using these statistical models that we have to understand what types of planets we expect to find. So this is most of a very large fraction. This is like 99.9% of all known exoplanets by its year, the length of its year on the bottom, and then its mass. And if we go forward, that's where the Earth exists. So we haven't found very many Earth-like planets, but we're trying. Really, really want to find one of those. And then that's where Jupiter would roughly be. So we've seen a few more of those. But you can see we have a lot of data of planets that are closer into their stars than most of the planets in the solar system, and a lot of planets that are bigger than Earth, even some bigger than Jupiter. So some of these are based on detection biases we have. We can't see the smallest planets because they have the smallest signals. We just don't have the strength to do that yet. But we can correct for these things using the math and statistics that we know and get a general consensus of what we expect any given planetary system to look like. And so with these predictions, we can then understand what type of planet we would expect to find when we search for these more planets in these systems. Will it be like Venus or Jupiter or the Earth, hopefully? So this is probably going to be the most technical plot I'm going to show here, and this is going to be going, but this is the Kepler 154 system. So this was one of the systems that is very well, or has been well studied because of the number of planets it has. So here I'm showing the year for each of these planets in terms of days. So the closest planet orbits at 3 days, so it just zips around its star, and then the farthest one orbits at about 60 days, so just a little inside the orbit of Mercury. But they're all very well ordered, so they have a very, consistent spacing between them, except for these two. And so my research then went and looked in and said, okay, if we only know about those 4 planets, where would we expect to find an additional planet in the system? And the biggest one we looked for was right there. So that's around 8-9 day orbital periods. There's another potential to find planets further out, but that's kind of expected in any given system. If you have a planetary system, you just keep looking further out. Like for example, with Planet 9 in the solar system, you just got to keep looking further and further out. So these are the 4 known planets at the time. It's a slight of a bit of a lie because there actually were 5 known planets. I removed one of them just to show, without knowing where that planet is, without knowing what it looks like, we can still determine where it is, and we can predict it to a very high degree of accuracy. And so when you put that planet back in, it matches exactly the predictions on where you'd expect to find it in the system. We can also determine other parameters about it, what its size is, how its orbit is tilted with respect to the Earth, whether or not we can see it transit in front of its star and see the starlight dip. You can make a lot of these different predictions just based on the characteristics of the other planets in the system and building up those statistical models to get the most likely or highest expected likelihood for those planet parameters. So I'm going to switch a little bit now to one of my other projects. This, for anybody who's a sci-fi fan out there, this is the Nauvoo. This is from The Expanse. This was a generational ship sent to orbit Tau Ceti, looking for, I don't know if there was a habitable known planet there at the time, but it was meant to go, send humanity into the cosmos. This is the node from the Rama series by Arthur C. Clarke, where there was also a civilization that built their space station around Tau Ceti. The Tau Ceti is a very well-known star for science fiction writers. It's very close to the sun. It's very similar to the sun in that it's just slightly smaller and is alone. It doesn't have any other stellar companions around it. It does have 4 known planetary companions and evidence for at least 3 more. So that's again here what I'm trying to show with this plot, similar to the one before. These red triangles are the planets that are known. Those yellowish diamonds are the ones that are suspected to be there, but have not enough evidence to prove that they are truly there. And my research shows that they likely should be there. If we have, given these statistics, given what we expect in a given system, you'd expect to find a planet at each of those positions in the system, along with an additional planet predicted to be in the habitable zone of the star. So if it were rocky, it could potentially have host life. And so this was a little animation that my advisor and I came up with for the system. So here, those are the 4 original planets that were known. So you can see them, nicely orbiting the star. You can see that there's nothing in the habitable zone. You just have those 4 going around. And so we took all that data we had from Kepler and all the other exoplanetary systems we have and said, okay, where would these planets be if they were to be found? And we predict that those 3 would be found where they were expected to be found. Where there was evidence for them to be there, that's where we expect them to be. We also predicted an additional exoplanet in the habitable zone. And so that's going to show up right in a second. There we go. So there's very, very weak evidence for this. It has not been studied in full detail yet, but that's part of what I'm trying to do going forward now, is determine if we can find that planet with current observing techniques. So yes, Tau Ceti is known to have 4 planets. It's predicted to have 4 more, and that one in the habitable zone could potentially harbor life if the surface conditions are right. So here I'll just end with my little, goal for the future, looking forward. There's a telescope that was just announced earlier this year that is being planned for the 2040s. It's the Habitable World Observatory. It's meant to take a direct image of a planet and look for signs of life in its atmosphere. Things like oxygen, carbon dioxide, ozone, methane, stuff like that, to determine whether or not there's definitive life on a flat planet. So it's going to search as many nearby Earth-like planets as it possibly can with this direct imaging technique and look for those signs in the atmosphere. But if you remember from previously, I showed there weren't that many planets in that part of the parameter space where we'd expect to find the Earth. So we need to find those Earth-like planets. We need to find more of them, especially nearby the solar system. That way we can actually observe them, because again, the limiting of the technology is the closer they are, the more likely we are to be able to observe them, and the better the signal will be. So, can use what I've been doing to then predict which of the nearby systems of all the star systems around us and planetary systems around us are most likely to have those Earth-like planets. And then we can prioritize current searches for planets to look around those systems, looking for planets that are of the same size and receive the same amount of energy from their star that the Earth does, to then send those targets to the Habitable World Observatory when it launches in 2 decades to search for life elsewhere in the universe. So that was it. That was my very end. Question over here. The question was, when was the asteroid belt discovered, or when was it listed along with the planets in respect to the Tedious-Bode law? It was known from early on, but the idea of there actually being a dwarf planet-like series was roughly around the same time as Uranus. It was at the 1700s. They were able to track these minor bodies because they are relatively close, right? Like, we can easily track Mars, we can easily track Jupiter, things that are roughly the size, or a little bit smaller than Mars, obviously, but like Ceres was able to be tracked from around that time, the 1700s, with a stronger, powerful telescope. Yes?
So, which agency is leading or planning for Habitable? Is it NASA?
So the question was, which agency is planning for the Habitable World Observatory? Is it NASA? And yeah, this was a recommendation from the decadal survey that NASA runs every decade. Ours was supposed to come out in 2020, but I don't know what happened that year. So it came out recently, 2022. And their recommendation was to build a telescope to search for the signs of life in planets nearby the solar system. Yes?
James Webb?
Choo-choo number 3. Sorry, can you say that again, please?
James Webb helping you at all?
Question was, is James Webb helping at all? Unfortunately, James Webb was not quite made to do this sort of science. It's an extremely powerful telescope and very good at everything it does, including looking for planets, or looking for signs of atmospheres on planets. Everybody wants to use it, and so it's very hard for someone to say, let's go look for a bunch of planets and just like look at all of them and see if any of them have signs of an atmosphere or life or anything like that. It's very much meant more for, we have other instruments who have looked for these sort of things, and then we have a definitive, like, this is really super cool and interesting, send that target to James Webb. And so that's what the TRAPPIST-1 system basically is. There's a bunch of planets orbiting a very small star very close to us that are all zipping around inside the orbit of Mercury, and there's a potential that a couple of them actually could even be habitable, similar to the Earth. And so the idea is then maybe to look at those with stuff like James Webb to then determine, could there be an atmosphere here, could there be signs of life at these ones? But that's really the only real system we have that like we could actually do that with right now with James Webb. The question was, how do you think we'd be able to detect the planet in the habitable zone around Tau Ceti? So the planets around Tau Ceti were actually found all via the radial velocity method. So it's basically the planet as it orbits the star, tugs on the star, and the star actually moves in the sky, and we can measure how much it moves and determine with good models what the star actually is like, what the planet's mass then is. And then you can measure the period of the signal and determine what the orbital year is. That would be the best way to do this because we didn't see any of the planets transit, none of them go in front of the star. And we have measurements of a Kuiper belt-like debris disk, something external to all the planets that's actually very large and very well characterized, that says that we're seeing the system at an incline to where we're thinking. It's not edge on, it's not face on, it's somewhere in between. And so we can use that to then determine what the likely masses and stuff of these planets are. So that would be the best way to go about it. Unfortunately, because the Tau Ceti is so much like the sun, the orbital period of that planet would be similar to a year. And the Earth, in a year, is moving around the sun. And so we have to take that measurement into account. And it's actually very hard to disentangle the Earth moving around the sun from another planet pulling on its star. And so there's an area of the parameter space that's actually very hard to measure simply because it's so close to the Earth's period. So that's one of the things we're trying to work on. It's kind of slow going, is figuring out how we can disentangle those signals. There's one more over there. So the question was, in terms of light years, what are the distance ranges in which you can accurately discover these? I'd say anything that what Kepler could discover. So, thousands of light years, depending on how far away the planets are, how big the planets are with respect to how far away they are. It's all depending on their signal. So if there's a bigger signal because the planets are bigger compared to their star, then they'll be more accurate and you can have a better chance of seeing them. I still think a majority of what we're going to find is going to be within, 100 to 500 light years probably, because in general, the volume of space gets so large and the amount of stars you have to search around that space to be so large that it's just really easy to focus on the close-in ones where there's just stronger signal and less stars in general to survey, that we'd be able to be extremely accurate in finding these types of planets.
Thank you so much for that excellent talk, Jeremy. So it is now intermission. We will have 20 minutes. It is now 8:04, so let's just call it 8:25. Be back here. If you're going to drink, please remember to tip your bartender. We have merch over here. Feel free to come buy merch or just come chat with us. Whoever won that trivia prize, whoever it was, feel free to come talk to us during intermission and pick it up. And I think that's it. So we'll see you back here in 20 minutes at 8:25. with John Barentine and Betty Maya Foote, who will be giving us some International Dark Sky Week trivia.
Hello, everyone. Ooh, microphones are kind of hard. I will try to not make it sound very bad. My name's Betty Maya Foote. Ooh. And I work with the International Dark Sky Association, which is born and raised here in Tucson, Arizona. And we are headquartered here, and we are a 501c3 that works for dark sky conservation and light pollution reduction around the world. And I actually took the job at IDA because I wanted to work with this gentleman here.
Hey everybody, my name is John Barentine, and yes, I did work with Betty Maya for a long time, and now I'm a freelance consultant here working in this subject generally, and we are going to be giving you some dark sky facts and asking you some fun trivia questions. Yeah, can we move this way? Can we move this back? There we go. All right, there's an annual event called International Dark Sky Week every year. It is going on right now through the 22nd of April. And so what we're going to be doing is, like I said, giving you a little bit of factual information about this subject, and then we're going to ask you some questions. So do you want to tell them how it's going to work?
I would love to. So Hayden, would you please kindly go to the next slide for us? Okay, so we are going to break up into teams. So find yourself a good trivia team. And you are going to need a smartphone for this, and you might need a dedicated team member to come up to the screen and scan this QR code, because we're going to be doing the trivia from our phones this evening. So if you can't get it from back afar, please come up and scan this QR code. And our winners tonight will get these very cute I Heart Dark Skies beanies. We have one for first place, one for second place, and one for best team name. So come up with a good team name. I'm gonna say if it's space themed, points. If it's funny, points. If it's slightly inappropriate, points. So best team name will get a hat, and then first and second place will also get a hat. And then my friends Marcos and Spencer over here are at the table that has a ton of stickers and brochures. So even if you don't win, you can take home some stickers and brochures as well. So has everybody been able to scan the code? Does anybody need help? All right, Hayden, go ahead. Okay, we're thinking. Well, maybe I'll just give some Dark Sky Week history while we're here. So International Dark Sky Week was actually started by a high schooler many years ago. She's like 30 now. Her name was Jennifer Barlow, and she was a high school student who was really passionate about dark skies. And she decided, you know what, we need a week. We need a week for dark skies where we really raise awareness about this issue, tell everybody about light pollution, and just celebrate dark skies around the world. So ever since she brought the idea to the International Dark Sky Association, I don't know how many years ago. Do you have any idea how many years ago?
20 years. It's 20 years this year.
20 years. We should have been celebrating that. Well, happy 20th year birthday party to International Dark Sky Week. And so if you are a high schooler here at a bar trivia, congratulations to you, and you could also make a difference in the world in the future.
Sorry for the technical difficulties.
Sorry for the technical difficulties, but it's going to be fun, so it'll be worth the wait. Sure, yeah, I can tell you guys about IDA. So IDA stands for International Dark Sky Association. I can't give away too much because there is a trivia question about this, but our work really is to empower local advocates around the world to make changes in their communities for better lighting practices and to celebrate and enjoy the beauty of the stars and healthy community-friendly lighting around the world. So here we go.
Awesome. So what we're going to do is we're going to give you, we've got a slide that'll have a little bit of factual background, and then we'll ask you a question based on that, and we'll put up a slide that has the question, but we'll also read it out if you are having trouble seeing it in back. And the main thing to know about light pollution besides the fact that obviously if you care about astronomy, this is an important topic, is that we as a species have really fundamentally transformed our world at night. And we've done it in a very short period of time. So what I'm showing you here is a composite image that was made by NASA using about 1 year worth of Earth orbiting satellite data. So they're looking down on the Earth constantly every night, passing over every part of our planet and taking images. And it's sensing light on the night side, so it's faint light. And adding up all these images over the course of the year, they were able to put together this mosaic as if it were simultaneously night everywhere on Earth at once, and also that there are no clouds. And the main thing that you see is that the continents stand out from the oceans pretty well because there's moonlight falling on the continents during some parts of the year. But the other thing that you'll notice is all of that, those kind of yellow dots all over the map that kind of fall where you think they would, that's humanity's light at night. That light is coming up out of off the ground through the Earth's atmosphere and is being detected hundreds of miles above the surface of the Earth. We now know that over 90% of people who live on this planet are somehow affected by this phenomenon. They live in places where there is what we would call artificial light at night, and many of them cannot see very many stars where they live, and this is increasingly the case because we are an increasingly urbanized species. So the world lights up in the places that you would sort of expect where the people are, but as I like to point out, there's not very much light here in sub-Saharan Africa, but there are 1 billion people who live there. So it's also telling us something about the level of economic development of people in the world. And so that leads us to our first trivia question. So next slide.
There we go.
All right, I just want to see everybody's names as they join the quiz. I like my beer how I like my skies. Good for the community. Monte Dobo. I don't even know. Do you know what that means? The Black Holes. Okay, Dark Dominion over Fox News. Space Specs. Logan. All right, is this all we have? We gotta have some more people joining here. 1, 2, 3, 4, 5, 6. One coming. One coming.
Professional astrologist.
Professional astrologist. Oh, I love astrology. You know how many times astronomers have looked down on me? Like, I don't care. I'm a Leo and I love it. Cats. P&P after a beer. I don't even know what that means. Hoppy. Astromeda. That one's good. Whoever did that one, yeah. I like that one. Cool. All right. Very nice. Anybody? Are we waiting for anybody else? No? All right. Go ahead, Hayden. So, question number 1. This was recently released in a paper in Science, the periodical journal that is very well respected. By what percentage, on average, has the night sky around the world been getting brighter in recent years? As a hint, this was using data collected from Globe at Night, which is a community science organization where you can just use your phone, look up at the night sky, and compare what you see to what's in the night sky. Okay, it looks like we have 8 out of 16. 9. You also get points for how fast you answer. So if there is a tiebreaker at the end, the speed of your answer will cause the person who was faster to win, if that helps at all. We got 2 more people in the back waiting for your answers. I hope Astromeda has their answer in. Alright, there's 2 people. I'm going to give you 5 more seconds. If you don't get it in 5, 4, 3, 2, 1. Do you guys need help? Does anyone need help? Alright, go to the next slide. So, okay, this is our guesses here. Mostly we're getting a 5% per year guess. So Hayden, next slide will tell us the correct one. It is 10% per year. So that means if a child is born today in a place where you can see 250 stars. By the time this child is 18, they will only be able to see 100 stars left in the night sky. All right, go ahead. Oh, it's me. Okay, so we're gonna talk about light pollution. I mean, who here knows like what light pollution is as like astronomers? Do we all know what light pollution is? Raise our hand. Okay, that's not like that many people. Maybe no one's paying attention, but I'll just tell you what it is in case you don't know what it is. So there's a couple different forms of light pollution, and the first one that we think of that obscures our view of the night sky is called sky glow. So that's when you're looking at a populated city or area, that dome of light on the horizon, that's called sky glow, and that reduces the contrast in the night sky, so those fainter celestial objects are washed out, like the Milky Way, like all the beautiful things we want to look at. And it actually appears that the light is coming from the night sky itself, when in reality, the light is coming from misdirected lights on the ground that are refracting through our atmosphere and causing that night sky to glow. Other forms of light pollution are glare. So who here has been driving down a lonely road, country road at night, and somebody has forgotten to turn their headlights off? It's really uncomfortable, hurts your eyes, makes it hard to see. You've all experienced glare. It can actually be a pretty big detriment to safety if you're trying to see into dark areas or see pedestrians under bright glaring lights. Glare is bad. And then finally, light trespass. So this is when light is coming from maybe these places, right? Like, I mean, who's working in these offices right now? Can they like turn their lights off or at least shut their blinds, right? Or other buildings, or, potentially a gas station. That light is coming out of the property onto your property, trespassing into your home, into your window, making it hard for you to sleep. So those are the basic three components of light pollution. So Hayden, you go to the next slide. And here's our next question. You can click it one more time.
Okay. So what percentage of light that's emitted by all these outdoor light fixtures serves a useful purpose? By that we mean that light ends up in somebody's eye to be able to see the things that they're trying to see at night. What percentage of that? Less than 1%, 15%, 35%, more than 80%. This is a tricky one. Should have had music queued up.
Yeah, we should have some background music. Okay, 13.
Almost there. 14, 15.
15, one more people. Yes!
Ah,
100%.
very good.
Good
All
job,
right.
you guys. All right.
So let's see the correct answer.
Okay, less than 1%. That's what we nice. We all think that.
It is less than 1%.
Good job, you guys.
In fact, it's a lot less than 1%. So there's some research that suggests that for typical lighting installations, that only 1 out of every 20 million photons actually ends up in the eye of an observer who needs that light to see at night. So we could do a lot better with the efficiency on outdoor lighting. Okay, next slide, please. So part of what that represents is energy waste. If you think about these buildings like the one behind us right here with all these lights that are on at night when there are no office workers in those buildings, and you think about then all of the cities around the world, I think this is San Francisco. I think that's a Transamerica building over on the left. You get a sense of exactly how much of that light is wasted. And we're differentiating between useful light and wasted light in terms of what is light pollution. When we are using that light and it's serving a good purpose and it's confined to the right space and it's the right amount and it's the right time when people are around to use it, we generally don't think of that as light pollution. But a lot of this is simple waste, and it turns out that that's a significant amount of the light that we generate. And on a global scale, we have reason to think, based on data, that about 1% of all of the electric generating capacity in the world goes to power lights like these that aren't benefiting anybody. And there's not only just the cost associated with this, but there's also an impact to the environment, because around the world we're still generating about 80% of our electricity with fossil fuels. So all of that wasted electricity is also added carbon emission to the atmosphere. And if we could just reduce the amount of waste by turning off the unnecessary lights and making better use of the lights that we do have and need, we would be able to avoid a lot of carbon emission in the process and reduce the impact on the environment. And so with that, next slide please. Our question is...
Yes, how much money does wasted outdoor lighting at night, escaping to space, basically lighting up the bottom of the International Space Station, represent in annual energy costs? And John, is this in the US or is this globally? This is globally. US dollars, global amount of money spent on wasted lighting each year. What do we think? And I forgot, what is the million metric tons of carbon dioxide?
It's roughly 600 million metric tons of carbon every year that's associated with lighting.
Okay. Way too much. Way too much. All right, we got 12. We're gonna give you guys 5 more seconds. 12, 13, 14, 15, 16. 4 more people. Come on, let's go. You know what? It looks like people aren't really doing it. Just make a guess at this point. Just guess. Okay, let's go to the next one. Oh, we did get 16. Nice. Okay, 100 billion is our main guess. Hayden, tell us what it is. 50. It is 50 billion annually, but that we could do some pretty good work with $50 billion, don't you think? And making our world a better place instead of spending it on light pollution. So we'll go ahead with the next slide. Oh, is this one me? Okay. So this is one of my favorite kind of issues surrounding light pollution, because I think it's one that doesn't really get talked about that often. But we can actually think about light pollution as a social justice issue as well. There is a certain percentage of Asian, Black, and Latinos in communities in the United States that experience more light pollution than white Americans do. And this image shows a project in New York City, which is called omnipresence lighting, which is basically round 2 of Stop and Frisk. This is their second best idea, which is pointing bright floodlights at housing projects all night long, which are powered by loud, noisy diesel generators. And the goal here is to reduce crime. But residents have complained about these lights, right? They have reported being unable to sleep, experiencing headaches. And to me, this really just shows how we use light, have used light historically, and continue to use light to reinforce a lot of the power dynamics of surveillance and control in our society. So if you go to the next slide.
So for some research that was published in 2019, which is so far in the United States, our only nationwide look at this issue, that research showed that Americans of different racial and ethnic backgrounds are exposed to different levels of light pollution. How much more or less light pollution do members of racial and ethnic minorities receive than whites? And it ranges from 25% less to about the same, 10% more, or 50% more. This is just the United States. Yep, this is the only country for which we have this data available. At 12, 13, we're almost there. 14. 16, all right. Let's see what the answers were. 50% more, a lot of that, you all converge on that number, and that is in fact the right answer. And that, as we know, because the estimates were made based on satellite data and the satellite data are incomplete, that's probably a lower limit for that number. It is likely higher. And the message here is we can do better as a society in terms of designing our outdoor lighting installations to make sure that we're not disadvantaging people based on who they are or where they live. Okay? All right, let's look at where we're at with the leaderboard. As you can tell, that's sort of a, that's yep. Cats, number 3. Darts and Indian over Fox News in 4th. And rounding out the bottom of the top 5, that is the Black Holes. Yeah, this is a great big 5-way right here right now.
But we do have a tiebreaker at the end.
Okay.
I wanted to do a dance-off, but
We won't put you through that. All right, let's go ahead on to the next slide. Okay, one thing that we know that artificial light at night has a big impact on is wildlife, and that's because all of the many plant and animal species that are out there in nature evolved in a world that for literally billions of years did not have anything other than natural sources of light like the sun, the moon, and the stars in their environments. And so because we've only introduced electric light in about the past 130 years, there simply haven't been enough generations of these species yet to start to really adapt to these high levels of light at night that they are now experiencing. And there are lots of examples that we could use, but of course, because we're having trivia at a bar, we thought we would try to make this alcohol themed. And so if you like margaritas or you like tequila, you should care about light pollution, because this fellow right here, which is a species of bat that's native to Mexico, is the main natural pollinator of the agave plant. And in fact, you can see this bat is in this picture who is going into these flowers to drink the nectar and pollinate, has got yellow pollen all over his adorable little face. The farmers of agave in Mexico rely on these bat species to pollinate their plants. It's something that the biologists would call ecosystem services. So we get all of this effort for free from these natural sources, and it's not just agave. A lot of our food crops rely on natural pollination as well, and the pollinators are very sensitive to artificial light at night. If the agave fields are lit or they're near lit locations, the bats will simply not visit them at night, and that is harmful to the agave population, and ultimately it's harmful to the bat population as well. And so that leads us to the next question, which is
about how many plant and animal species have been studied for effects from exposure to artificial night lighting. This is globally, right? All around the world, how many species have been studied with a dedicated means of understanding artificial light at night on that species? And just so you guys know, John has read every single one of these studies. He is probably the smartest dark sky person you'll ever meet on the planet. People refer to him as the Dr. John Barentine instead of just John Barentine. So we got one more team waiting for a guess. All right, 16, go Hayden. Okay, 150 is our number one guess, and the answer is that answer. Good job, guys. Very well done. This is an educated audience for sure out here tonight. Well done, team. All right, let's go to the next slide, please. Okay, so this slide is meant to talk about a lot of the benefits that can come from dark skies, and one of the main benefits of protecting our night skies is that communities who have beautiful night sky resources can benefit from what is known as astrotourism. And we get a lot of that here in Arizona. We get a lot of that in the Four Corners region, in the Colorado Plateau, and actually all over the world. And it's not just something for places with naturally dark skies. Planetariums are a form of astrotourism. Full moon walks, right? You can see all the planets in places with light pollution. So I think as humans, right, we're intrinsically connected to and pulled to the stars, and we all want to have those experiences. We all want to go see the beautiful night sky. And what's really, really cool about astrotourism is that in order to attend a night sky program somewhere, you have to spend the night. So people who are coming to your town or your community to go on your full moon walk or your star party or your nocturnal wildlife safari, they're spending the night in your community. So they're going and buying a hotel room, they're buying dinner, they're buying breakfast, they're probably buying more souvenirs because they're around more souvenir shops, and they're getting to know your community better, and they're not just passing through and getting their Instagram shot and moving on. It's a really positive form of tourism, and it's one of the emerging trends of ecotourism. So if you go to the next question. There was a study done by the University of Missouri, right, that looked at astrotourism on the Colorado Plateau specifically. And it had a number here, which you are trying to figure out, that how much tourism revenue is Dark Skies expected to generate on the Colorado Plateau by the end of the 2020s. So is it 10 million, 100 million, 850 million, or 6 billion?
So is it for just a decade or like cumulative?
Yes, for a 10-year period from 2020 to 2030. Yes.
But we've had a team join. We're up to 17 now.
17, we got new
Very
people.
nice. We're almost there. 16. One more team.
17-ish.
Possibly.
So we just keep waiting for them. Who's team number 17? Say you. Alright, let's just go.
Let's go ahead and see the answer.
Okay.
A lot of people are guessing 850 million, 100 million. So show us the right answer. 6 billion, billion with a B, and supporting over 3,000 jobs. So we're looking at a more educated workforce in order to be able to deliver these programs. And there are even people who are small-time entrepreneurs that are beginning to make a living off of this in the Four Corners region. It's a very definitely a growing part of the local economy, and all it takes to sustain this is to keep what you already have. The challenge is to make sure that as we grow the infrastructure to enable more visitors to come to these activities, that we don't bring too much light that spoils the resource that they're here to see. Okay, next please. All right, so Dark Skies has even made its way into popular culture, and we're going to show you a clip from this next, and we hope that this works. Our question for you is, what long-running cartoon series features an episode about light pollution entitled "Excuse Me While I Kiss the Sky"? Miss the Sky, excuse me, Miss the Sky. So the possible answers are Recess, The Simpsons, The Teenage Mutant Ninja Turtles, and King of the Hill. This is almost a gimme.
Is it? It's hard to make it kind of hard. Who's number 17? Who are you?
Go ahead. All right, most people guessed The Simpsons, and that is in fact the correct answer. Who here has actually seen this episode? Who seen this episode before? It's really good. All right, go to the next slide and see if you can get this to play. Oh, there's no sound. Can you press the closed caption on the bottom?
Let's see, hang on.
For eons, people have gazed at the skies and seen into their souls.
There you go. I mean, we all know Lisa is going to be the cool one who knows what light pollution is. And I don't think our internet's that great, but I would encourage everyone to watch this episode. There's also an episode of Hey Arnold that addresses light pollution as well that I have not seen. But choo-choo, everyone. Choo-choo. Cheers to The Simpsons and light pollution and Dark Skies.
Okay. So, a result of all of this increase in light pollution around the world in the last 130 years has been a social and even political movement that is now more than 50 years in the making. And what I'm showing you is one of the earliest references that we can find to the term light pollution in the mass media, which dates to the very early 1970s. This is an article in the New York Times from June 1971 that was talking about Tucson and the development of the astronomy infrastructure in and around Tucson, which already by that time was under threat due to the city lights of Tucson itself. And people have been observing the effects of artificial light at night on the environment for much longer. The earliest references that we can find in history are to some Roman authors who saw and wrote about the effect of oil lamps that they ran at night drawing insects. The modern concept of light pollution really dates from about the 1950s, and it originates in Flagstaff in northern Arizona, where there are also a lot of observatories like there are here in around Tucson. And in 1958, the city council in Flagstaff enacted what they called the searchlight law that was meant to reduce the effect of searchlights that were used for advertising purposes on the observatories. Our city, Tucson, we think, was the first city to enact a comprehensive outdoor lighting policy, and that was in 1972. So shortly after this article right here. So that tells you something about how long people have been thinking about this problem in Tucson and trying to do something about it. And Betty Maya mentioned at the top about the origin of the International Dark Sky Association, which is based right here in Tucson as well. So that takes us to our question, which is, in what year was IDA founded? So think about what we've just been talking about with this historical perspective. So your possible answers are 1988, 1970, 1995, and 2002.
Should we tell them who founded it? I feel like it's a pretty interesting story. So it was Dave Crawford, who was then the director of the Kitt Peak National Observatory, and his friend Tim Hunter, who was a family physician. And they both separately came to the understanding of the detrimental impacts of light pollution through their work. Dave through his work at the observatory, and Tim through his work on family medicine and understanding how light impacts human health. So they came together and actually created the International Dark Sky Association from two very different perspectives, but kind of uniting a lot of the reasons why we care about dark skies and light pollution. Oh, we got 18 now. 18 now. All right, people branching off. Are they mad at their team and then like want to do their own thing now? We only got 13. This is just a guessing game, y'all. Give it a good guess. 88, 70, 95, 002. Give you a couple more seconds. If you don't answer, then you have missed your opportunity. Go ahead. Okay. Good job, guys. Well done. 1988. Very well done. Correct answer. All right, John, now I'm turning it back over to you.
Okay, and to continue the theme of Tucson being a leader in outdoor lighting, we have one of the most advanced street lighting systems in the world, if you can believe that. And I say that because of our almost 20,000 streetlights in Tucson. They are all very carefully engineered and controlled so as to produce the least amount of light needed to safely light our streets, but also support dark skies in terms of reducing the impact on the observatories that are nearby. This was a conscientious decision of the city when it converted its old lighting stock from an earlier technology to LED lighting a little over 6 years ago, and it involved complete replacement of those nearly 20,000 streetlights. And in the process, the goal was to ensure that the new lighting system would not yield more light pollution and more impact to the observatories. There are very few cities in the world that have done this, much less as successfully as Tucson has done. And the result of this project is not only protecting dark skies for astronomy and space science in southern Arizona, but also a reduction in cost to the city It takes less electricity to run these lights, and as a consequence, the city is saving money and limiting carbon emission as a result. So that leads to our question for you, which is, by how much did Tucson's light emissions to space change after it converted its street lighting to new white LED fixtures in 2016? Oh, we got most of them. We got 15. That's pretty good. All right. You know the answer to this. The light emission from the city actually decreased in this process. You might not know it if you've lived here long enough, but our street lights are much less bright than they used to be about 10 years ago with a different lighting technology. And we measured this difference from space and found that the city's light emission had dropped by about 7% during this period of time.
Oh, the black holes. This is it. That was our last question. Who are the black holes? All right, you guys get a beanie. Come up here and get your beanie. Congratulations. Who's number 2? Who's Logan? Who's Logan? Where's Logan at? Oh, is Logan online? Logan, I'll give you a beanie another time. All right. Oh, choo choo. I got one more set left. Choo choo, guys. You know what? Actually, Logan, Katz, Montedobo, and P after a beer are tied. So, is anyone willing to do a dance-off for the tie? I mean, if you're willing to do a dance-off for the tie, yeah, we got a dance. All right, okay, we got some dance-offers up here. All right. So, bring it. Can you guys play some music? I can play it on my phone.
Oh boy.
I can hold on my phone.
If you want to connect to there's Bluetooth on the speaker.
There's Bluetooth?
Yeah.
Okay, let's put on some music.
I don't think
Really didn't think
I
we were
am.
gonna have a tie.
I don't think we ever actually set that up.
We didn't think we were going to have a tie, much less that people would actually want to do the dance off.
I was hoping. I was really hoping. Okay.
I think there might be a button we have to press.
Hayden's Max and Pro.
No,
Accessory. Or BLE.
yeah, that kind of. That's
Okay. So does anyone have a good recommendation for a dance-off song? Macarena? Bad Bunny. Did someone say Bad Bunny? I like Bad Bunny. Okay, let's go. Let's see. I feel like I gotta have some good ones on here. How about some Perreo Daddy Yankee? Oh. That'll work. Oh.
Okay, so you're one of these teams. Send your representative up front.
That works. Yeah, see, it wasn't playing. That's the same problem.
No one else knows who won. Nobody else? You won. No one else knows.
Watch our tables, please. Please don't die on our back.
What?
Please don't die on our back table.
Okay, you both get one.
Everybody wins.
Everybody wins. Astromeda, you gotta give me your info. I'll give you a beanie because you win best name. Honestly, thank you guys for that so much. I did not think Space Draft's crew was going to be down for dance off, but I'm very, very proud of everyone here tonight for this. So you can go to the next slide, and we kind of have some just ways that you can get involved and continue to hang out with John and I and talk about Dark Skies, because it is quite a good time. I hope you guys had a good time with us. We don't want this to end, and my main job with IDA is running our Dark Sky grassroots advocacy program. So We have a Dark Sky Advocate Network that is a global network of dark sky advocates around the world who all do incredible work to protect the night from light pollution and celebrate the beautiful night skies around the world. So if you would like to join, this QR code will take you to a very simple web page with a form that you just basically sign up in less than 30 seconds, and you'll be invited to, we have monthly trainings on different dark sky topics every month that are really action oriented, that get you involved in your community. We also have another set of monthly meetings where we talk about just a random topic in dark skies. In fact, we have one tomorrow, and we will be hearing from Travis Longcore on the ecological impacts of artificial night sky brightness. And we have an online communication platform where you can chat with and connect with advocates here in Tucson, as well as in Serbia, New Zealand, and Tajikistan. Like, there's some people from some crazy places who are doing dark sky stuff, and it's just really cool to be involved and see what's going on around the world. So would definitely encourage you to please join and support IDA and support our work locally here in Tucson. It's basically me and John and like 2 college students right now, so we need help. So please help us. And you can go to the next slide. And Spencer, wave your hand. This is my good friend Spencer, who I actually knew from when we both used to live in Colorado together. Now we both live here randomly. But he is a park ranger at Saguaro National Park West, and we are doing a star party on Thursday, another celebration of International Dark Sky Week, and it should be super fun. We're gonna have, like, someone's gonna lead like a Sounds of the Night walk. There's gonna be telescopes. There's gonna be like a Saguaro star silhouette art station, and there's gonna be Tohono O'odham person speaking about star stories. They can't tell all the stories because it's not winter, but it should be a really, really cool event, so we would love it if all of you could join us for that. And I think that is the end of our talk, so thank you, and I will let John say thank you as well.
Yep, thank you for coming out tonight. Thanks to the people at Space Drafts for having us, and enjoy the rest of your evening.
It has been my life goal to be at Space Drafts as a speaker, so thank you for making that happen for me. I can die happy now.
Oh, stickers! Stickers over here.
Oh yeah, we have stickers and brochures and flyers over here at the table with Betty, Maya, and Spencer. So please come visit us on your own.
Thank you so much for that amazing talk and very fun dance off at the end. Thank you all for joining us here tonight for Space Drafts 86. Our next show will be on May 16th, I believe. Can someone please check me on that? It's third Tuesday of May, May 16th. So please come join us for that. It'll be at 7:30, like normal. Tip your bartender on the way out. Come chat with us, buy our merch, and see you next month.